Hey, welcome everyone to today's session on building real-time retrieval augmented generation for financial data and news. I'm very excited to have a chance to share with you what the teams at Microsoft, Unstructured, and Bytewax have been building together for the last few weeks. And in this workshop, you'll have an opportunity to learn not only some of the key technologies behind the system that we built, but also we're going to be sharing with you some code snippets and showcasing how you can reproduce this kind of solution yourselves. So I'm going to go ahead and start off by sharing our goals for the day. So our goal for us is, of course, to build retrieval augmented generation at a scalable and production-ready level with a focus on real-time data updates. The focus for us, of course, is going to be on unstructured information. And the goal is going to be for us to incorporate the ability to retrieve information on a real-time basis, extract the insights in the text, apply embedding models that are deployed at a production level, and then populate production-ready vector databases that we can then use to retrieve the information from. Our goal is going to be to combine the services from Unstructured to process information that's coming from web pages, images, and text, and to use Azure AI services to deploy and manage our RAG pipelines. Lastly, we're going to be sharing with you how we can incorporate all of these different pieces together through Python, and we're going to be sharing a little bit more in depth how we built some custom functionality, not just for the RAG and indexing systems, but also for the real-time analytics front end. By the end of this workshop, you should feel comfortable with some of the key concepts behind architecting and deploying real-world RAG systems. And you should have an understanding for how to implement and replicate the solution either at home or at your work setting if Unstructured and Azure AI are services that your company or your team works with. In terms of the agenda, so we're going to start off by telling you a bit about the problem statement, what it is that we're trying to solve. Then we're going to have an opportunity to hear from our partners from Unstructured, Microsoft, as well as Bytewax. Each of our partners will have an opportunity to tell you about their unique solution and the technology. Once we've had a chance to listen to the partners and understand the technology that they're bringing, we're going to transition into the application itself, namely how we work together to integrate all the different technologies into a unified system that has one goal, which is to update it production-based vector databases in real time. Afterwards, we'll have a chance to do a bit of a code demo so you can see how these different pieces interact with each other. And then we'll talk a little bit about, what is the purpose or the use case? What is basically the problem that this is helping us achieve? We will be monitoring your questions in the chat. So if you have any question, please make sure that you use the chat feature. You can start right now if you'd like to network, if you'd like to get to know your fellow peers. You can always drop a little message and say, hey, where are you joining us from? What about the workshop caught your attention? And maybe as an icebreaker question, what is your favorite snack? So we will be monitoring these questions in the chat and answering, but at the end, we will also have times for some live Q&A. If you don't feel comfortable unmuting yourself or being on video, we are recording the session. You're welcome to drop the question in the chat. And again, we'll address it either during the workshop via text or during the live Q&A session. So I do want to start by telling you about our speakers and the people behind this workshop. And I want to tell you about how we got together and worked on this solution. So Shagun, Sharma, Zander, Nina, and myself had an opportunity to work together asynchronously, as well as through an engagement week through the AI Innovations Lab. And we had an opportunity to put together a proposal for the kind of problem that we want to solve. Our focus, of course, was, we've heard lots about this idea of retrieval augmented generation and how we can leverage LLMs to retrieve information and generate more nuanced responses. But of course, we still think about this problem in the context of data science, where the data changes on a regular basis. If we think about data that comes from IoT devices, or if we think about data like financial news, that information doesn't stop this minute. We have news coming in every second, every minute, every single day. So the purpose of this engagement for us was to identify ways we can connect different technologies. And, within the context of RAG, there's a huge variety of technologies out there. We have LLM orchestrators, we have vector databases, we have embedding models, we have large language models, and then we have highly specialized tools like Unstructured, where we can focus on different aspects of RAG and fine-tune those aspects to make sure that our systems work better. For this workshop, the big focus is going to be on indexing pipelines and the process of extracting information from unstructured sources and populating a vector database at a production level. So we had a chance to work on this different piece, both with a real-time extraction and real-time vector DB population. So now I want to tell you a little bit about our speakers and who the people behind the engagement were. So Zander, our CEO at Bytewax. So Zander is a seasoned data engineer who has founded and currently helms Bytewax. He has worked in the data science space since 2014 at Heroku, GitHub, and an NLP startup. And before this, Zander attended business school at the UT Austin and HEC Paris in Europe. Joining us from Microsoft and the AI Innovation Labs team, we have Shagun Sharma. Shagun is a data scientist at Microsoft via the TCS program. She is a highly skilled data scientist and AI engineer with over 5 years of extensive experience in the field of NLP. And for almost 4 years, she has been a pivotal part of the AI Co-Innovation Lab. This is a lab where we had a chance to engage for this workshop. This is an initiative that has led multiple customer engagements around the generative AI use cases. She has had a chance to work in Redmond, Montevideo, Uruguay, and San Francisco, California. And she has built more than 15 proof of concept projects leveraging Azure technologies, including Azure OpenAI, Azure AI Search, Document Intelligence, LangChain, and other tools. Joining us from Unstructured, we have Nina Lopatina. Nina is a staff developer relations engineer at Unstructured, where she helps customers make the most of their unstructured data for retrieval, augmented generation, and other large language model use cases. Nina has been primarily working on multilingual language modeling since 2018. And in this span, she has worked on language classification and generation. Throughout her career, Nina has focused on the data and LLM needs to improve performance and reliability. And for myself, I am joining as a senior developer advocate at Bytewax. My background is in mathematics, and prior to working as a developer advocate, I worked as a data scientist, both in the non-for-profit and the for-profit spaces. So we're very, very excited to talk with you today about the solution that we put together. And with this, I'm going to go ahead and segue to our next session. So for the next few moments, we'll have a chance to listen from each of our speakers. Each of our speakers will tell us about the offering. So we're going to have a chance to hear from Zander about Bytewax, what it is and what you can do with it. We're then going to hear from Shagun. Shagun is going to tell us about what the Azure AI services are and what Azure-based services we use for the solution. And then we're going to hear from Nina, and Nina is going to expand on the applications and functionalities from Unstructured that we implemented throughout the workshop. Once we've had a chance to hear from our speakers, we're going to go back and transition into how we integrated them together into the architecture and solution that we're going to be presenting with you today. So with this, I'm going to pass it over to Zander. Zander is going to tell us about Bytewax. So over to you, Zander.
I need you to, oh, there we go. All right, everyone. I'm also excited to be here. Thanks, Laura, for really pulling all of this together. I'm going to tell you a little bit about Bytewax. For those who aren't familiar, Bytewax is an open source Python native stream processor. And what does that really mean? I'm going to see if I can use the animation. I like to use this image to our animation to capture what it is. So you have data living in disparate places, and as Laura mentioned earlier, it's continuously being generated, and Bytewax is a tool that you can use in order to process that data. So you can kind of think of it as this glue or middleware layer where you're able to connect to all of these different data sources, edge devices, events, apps, etc. Very commonly, it's Kafka or something Kafka compatible. And then you can do these operations on top of that data, enrich, filter, aggregate, transform, window, join, branch, and write it out to different output sinks. So Bytewax is Python native. So what's special about Bytewax comparison to if you're familiar with Flink is it's very easy to use. So it's pip install and then run your run your file and you're going with streaming data. You're working with streaming data. What is Bytewax holistically? I just kind of tried to put this little thing together to provide people with an understanding who haven't seen it before. So Bytewax first is a open source project. That's how you write what we call data flows. Those are essentially services to process data. And then Bytewax also has a bunch of other capabilities as well that make up this entire platform. So we have connectors and operators that extend data flows that we call modules. We have Wax Control, which is the command line tool to deploy Bytewax data flows, and then we have the orchestration and governance layer, which is the which we call Bytewax platform in totality, and that's where you can scale and you get additional benefits like recovery and disaster recovery, authentication, etc. So last little bit of this pitch, and then I'll move on to someone else, and we can get moving into code sooner. Bytewax is just plug and play Python. For those of you who are familiar with the alternatives, which would be Apache Flink, Spark Structured Streaming, and some of those others, if you have used those, if you haven't, it's a lot easier to use, especially if you're in the Python ecosystem, which we often are if we're doing machine learning or AI. It's very extensible and interoperable. We made it to be as flexible as possible, so you can connect it to write custom connectors to virtually anything, and you can run it virtually anywhere that Python runs. And then with the entire platform offering, it's scalable and secure. So all of this culminates in a 5 times faster production and 10 times a 10% or 10 times smaller footprint than Flink, or 10% of the footprint of Flink. So it's easier to use and cheaper to run. That's what that means. All right. I think I'll stop there and turn it back over to the next person. Shagun, I think that's you, right?
Yes, we should have Shagun next to tell us about Azure AI services and the technologies we incorporated.
Thank you. Hi, everyone. My name is Shagun Sharma. I am the lead data scientist in the AI Co-Innovation Lab here in Redmond, Washington. I can briefly talk about, just to introduce you to the lab in which I work. It's basically, we have a physical location here in Redmond where we run this lab and have multiple customers coming to accelerate their business solutions around generative AI. It's kind of a personalized one-to-one experience with our dedicated lab experts. And we offer a broad array of services and personalized engagements that are, tailored to your particular projects. And briefly speaking, this program is free of cost to the customer. The only thing is that we work in the customer's tenant. So basically, the only cost that you incur is your Azure subscription. We are primarily focused in building generative AI solutions with Azure services right now. And the lab is in existence since almost 7 years now, I think, maybe more than that. But I'm part of that lab from last 4.5 years now. I can switch to the Azure AI services that we have used in the Bytewax RAG architecture here, but I can share a link in the chat, Laura, maybe in the chat, for our lab program here, and later on I'll share few links to just introduce you to services in case if you want to go back and learn more. So first I'm going to talk about let me share my screen. Okay, you guys can see my screen, right?
Yes.
Okay, great. So I can quickly walk you all through the basically how we can create these two services. So Azure AI Search and Azure OpenAI Services are the two services that we have used in the RAG architecture for the Bytewax use case. I can quickly show you maybe just one service, how you can create. You can go to the marketplace and just click on create service. You can choose your subscription, choose the resource group that you have created for your project, and then give a service name to your AI service. Okay, And then for the scaling option, you can choose however replicas and other storage settings you want to choose. Networking, you can have it public or you can have a private endpoint added to your service, and then basically just go and review and create. And this is as simple as that, to create a resource group to create the service in your subscription. Once I click create, I will see a service like this. I have already created it under my resource group called this. So this is a sample index that you would see once you have your documents populated. So basically the concept of the index and indexer in Azure AI search is where you have your own content populated to the service with certain fields, for example, the schema. So similar to what we have kind of SQL schema or any other schema for our data, you can define it via Python SDKs or REST API calls in JSON format. So basically, I have defined this schema that I want to have these fields and the type of fields. And this is the main thing here. We have a field name called vector, and you see if the dimension is 1536. This is basically using the text ADA 002 embedding model to generate the embeddings on the content field here and storing it in the schema. So this is the field which is holding the vector representation of our data. And in this, basically, you can have the inbuilt vector profiles which can directly connect to your Azure OpenAI service. So if you look here, I have my profile generated, which is connected to my Azure OpenAI resource, and it is basically used to generate embeddings on its own. So I don't have to run other code explicitly to generate the embeddings. And this is just a very basic search explorer on your index service. If I search anything, basically it will give me, sorry, I might have to switch it. But basically, when you click on search, you will see the relevant answers based on the semantic meaning of your question, and you will get the search score for each of the content, because I have this field, which is the main field that I want the data from. Azure AI Search, basically, it was earlier known as Azure Cognitive Search, which provides secure information retrieval at scale over your user-owned content in generative AI search applications. You can treat it as a vector database. You can perform vector search, full text search, hybrid search over a search index. You can integrate data chunking and vectorization on its own. You can, do rich query syntax for vector queries, text search, hybrid queries, fuzzy search, and other type of searches. It provides the Azure scalability and security basically on your data. And architecturally, if you think it's kind of a search service which sits between the external data stores that contain your unindexed data and your client app that sends query request to a search index and handle the response. There are few key concepts. I don't want to go through each of them, but I just want to show you quickly one major one, which is a very good feature in Azure AI Search. There's a concept called skill set, and you can have multiple skill sets. Right now, I'm showcasing two, which is a text split skill, which basically chunk your data depending on the split mode. For example, right now I have split mode as pages and maximum length of 2000 page overlap 500 tokens. And this is a split skill which can chunk your document directly, so you don't have to explicitly write code to chunk your data. You can just add the skill set from the portal itself or through Python SDK and other SDKs. The other kind of skill set is basically the Azure OpenAI embedded skill set. Again, you don't have to run explicitly to generate the embeddings. You can directly point to your model in your Azure OpenAI, which is deployed in your Azure OpenAI, and it will automatically generate the embeddings for your data. And it will upload that into your index here. I can, again, I mean, it's a vast service. I can keep going, but this is mostly the major things you should know about the Azure AI search. I can move to the the Open AI service here. So basically, this is how it looks like on the portal. And what is, if I have to talk about what is Azure OpenAI service, is it's basically the Azure OpenAI service provides REST API access to OpenAI's powerful language models such as GPT-4, GPT-4 Turbo, Vision, Dolly, embedding models, all the models basically. And these models can be easily adapted to your specific tasks, including content generation, summarization, image understanding, natural language. And again, you can access these models through REST APIs, Python SDK, or even the web-based interface in the OpenAI portal here. This is how the portal looks like. Um, you can have all the completion, chat, Dolly models, and assistant is a new feature coming up. It's right now in preview, and you can see all the deployed models under your subscription here, type of models that you are using. And this is kind of the playground, how it looks like. And this is just the playground. You can, once you run this basically the question, or
Yeah. I just wanted to grab my plug.
Sorry
I'm
about that,
sorry?
Shagun, continue. It was, I muted them, just continue, please.
Okay, no worries. So here you can select the deployment names from your available deployed models. You can change the parameters, temperature, top key, top P, stop sequence, frequency, and all other things. And you can directly, if you are satisfied and if you want to run it in your Jupyter Notebook or Python or C Sharp, anything, you can just import this. You have the endpoint, your key here, and you can just copy from here, and it will run the code for you. You have different options. You can run it in JSON, Python, C Sharp, Curl, Java, Go, all these things. But this is just a playground. This is just to explore. You can utilize it as much you want. One feature that I want to talk about is the content filtering here. So content filters, basically, it is the additional capability that Azure is offering on top of your models to protect your data from, to protect your basically the models or the solutions that you are building with utilizing these models. It helps in defining if it is, if somebody is misusing your models, if they are trying to jailbreak your prompts, or if they are doing like direct or indirect attacks. You can probably have it set up in this studio, or maybe in the content filter option on your deployed model. So there are different categories in risk categories like hate and fairness, sexual violence, self-harm, and you can get those in the form of your responses also, and block the response in the final response to your user. You can control it in both ways. You can control it at input level, you can control it at output level. um, Prompt shield is another one good capability to stop the jailbreak attacks, like I said. And in fact, for indirect attacks also, directly, like cross domain prompt injection attacks or indirect attacks. And um, this so the Azure OpenAI, so we have used this Azure OpenAI embedding model basically in the Bytewax architecture, and maybe Laura can talk about it when she explains the solution. So we are utilizing that model for generating the embeddings, and we also have the small language model, large language model in the Azure OpenAI studio right now. This is basically overall very briefly, but covering all the important points from my end on these two technologies. I think I can hand it over to
Just
Nina.
1 second. Yeah, so before we do that, so I want to provide a bit of context. So as Shagun mentioned, if you could stop the screen share for a bit. So we're going to be showing you how you can connect to these Azure services and leverage both the embedding, and apologize for the background noise on my end. What we're going to be showing with you during the showcase is how we connected to the Azure LLMs, the Azure embedding models, as well as Azure AI search through our Python scripts, and connected them along with Unstructured and Bytewax. So when we get to the solution piece, you'll have a chance to see us populate the vector DB in real time with our scripts. So thank you so much for this, Shagun. You don't have to, there's quite a bit of setup that we need to do to get the service going, but what we've done is we prepared the repository, which we'll share in a bit, with the instructions to set up these services and how you can connect to the scripts. Before we do that, I'm gonna go ahead and pass it over to Nina. So Nina is now going to tell us about Unstructured, and in particular, the functionality and basically an overview of what Unstructured does and how we can leverage it for processing text from web pages, images, and PDFs. As before, once we go through that piece, we'll have a chance to see the scripts and how we incorporate it into our real-time data flow. So Nina, over to you.
Thanks, Laura. Thanks, folks, for joining this workshop. And I'll just do a quick overview of Unstructured and what we do. So I'm Nina. I'm a staff developer relations engineer. And overall, we're a Series B startup. We have an open source repo, API, and platform. And there are lots of folks using it. So if you're not familiar with it, here's your chance to learn a little bit about it. We get your data LLM ready. We support a bunch of different formats, mostly images and audio files, and we've got video in the works as well. More file formats that we can fit here. So in our platform, for example, you would have your connector set up for any one of these major systems of record, including Azure and others and more that we can't list here. You can have all kinds of different files in them. And then we'll have a pipeline that will convert it to JSON and then chunk, summarize, and embed it, and then deliver it to the storage location of your choice. You can have any, I think, of the major vector databases or cloud storage or something. And so if you're going to be working on prototypes, you can use our open source repo. And then for production, we recommend using either the API or the platform, which is currently in beta. And behind the scenes, we're kind of taking a large variety of different file types, language, image, audio, and we're extracting the text out of them. And we have trained our models to work with a heterogeneity of document layouts. So, you know, I'll imagine every kind of slide layout you've seen or table or something. That's kind of a lot of what we specialize in. And so in this workshop, we're going to be extracting tables from image documents specifically. And we also look at things like reading order detection so that we can preserve that reading order, which could be different based on the document. And then we atomize these files into elements, which you'll see in the code. So these elements are chunks that are semantically relevant. So we'll have titles and subheadings and footers. And so we'll be able to, when we chunk the data, to preserve these kinds of meaningful relationships between the data. And we also include a ton of metadata, really any metadata that we can grab from that file as we're parsing it, including if something is a continuation of a previous piece. And so then what we output is going to be this chunked text plus all of the metadata. And here are some examples of how it works in action. So let's say you have a PDF. It will convert it into this nice JSON over here, which will then be machine readable. And you'll separate the title and have all of this different metadata. And then you'll have narrative text in a separate index in the JSON. And that, for example, here is the abstract from this document. And you'll be able to link everything together, downstream as you want by having both the parent ID of the full document and the ID of the element itself. And we actually have a paper out on semantic chunking, since this is a method that we have developed internally. If you want to read the paper, here's a QR code. And so other things that we include is we'll track which text is emphasized or bold in the text, because that can sometimes be meaningful. So here the abstract, for example, was emphasized. And we actually employ a number of different strategies. So we have generative models, high res, and fast. And so fast would be for something like a document that has text. High res is what we're using in this workshop because we have images. And so we're using this high res extraction, which is a little bit slower and more expensive, but that's going to extract text from images. And then we are also in the pipeline, including generative models that can then provide captions for images and things like that. And that would be the slowest process. And so we want to combine all of these different elements because obviously it would be over-engineering to use a generative model to extract text from a Google document. And so we have these 3 different strategies that can be selected based on the documents that you're parsing. And just measuring our performance, we think a lot about how many words are missed, if the text order is preserved, the natural reading order. And so compared to an alternative Gen AI solution, we're missing a very small fraction of words, whereas if you're missing 24% of words, you may be kind of losing the whole sense of the document. And similarly, the text order we're preserving is significantly higher than other solutions. So yeah, what we do is ingestion and pre-processing for Gen AI, and that's all we do, and that's what you'll see in the workshop. If you have any questions, feel free to drop them in the chat here. Thanks, everyone, and I'll turn it over to Zander.
All right, thank you so much, Nina. So as Nina noted, now that we've had a chance to see a little bit about each of the different solutions, our next goal is to show you how we integrated them together using Python. So Zander is going to show us, and he's going to talk to us about the overall architecture that we're following, and then Zander is going to zoom in on the ingestion piece. So Zander, if I'll pass it over to you.
All right. Yeah, I'm going to talk about the ingestion piece only in this part, but I'm showing you the whole architecture diagram so you have an idea of what that means. Right, hold on. There we go. Okay, so the ingestion piece is oftentimes in an architecture or any architecture, you want to separate concerns. You want to have some sort of durable storage layer, whether that be your database or whether it be some streaming storage or transport layer, and then the actual processing code. And this is so that you have some redundancy in your whole system if things fail, and so it's replayable, et cetera, et cetera. So what the ingestion pipelines are going to do is we're going to go and find a bunch of unstructured data, and we're going to pull all of that in, and we would put that into Kafka. For this example, we're going to just comment out the Kafka and would write it out to a JSON lines file, and then it can be used kind of more easily in the workshop. But ideally, you would have, when you're working with real-time data sources, you'd have some sync that you write to after you consume whatever data sources you're consuming from, like Kafka, that can work in real time. One additional benefit to something like Kafka, and there's many Kafka API compatible services. So there's like Red Panda, WarpStream. Microsoft has a hosted Kafka. They also have Event Hub is the Microsoft service that has a Kafka compatible API. One other benefit is that you can have multiple consumers. So if I read the data once, all of the SEC data, all of the financial news data, all of the stock market data into Kafka, then I can have multiple consumers consuming from that. So that's one other reason we split out the architecture in this way. We could have different embedding pipelines, or we could have alerting services and all these other services running off of one topic, and we're not all consuming from the actual source of the data. So financial news changes all the time. It's changing right now. And there's structured and unstructured data. As you're all familiar with the stock market, and you're probably familiar with news, but you might not be familiar with SEC filings if you're from outside of the United States. And that's what we're going to be using in this ingestion. SEC filings are basically anytime well, there's many different types of filings, but there are a bunch of company-related information, whether it's an individual buying a lot of stock in a company, an individual selling, or a company issuing stock, or a company writing reports about how the financials of the company are. There's many different types of filings, but it's a ton of information. And it's updated throughout the day. And there can be really important information, like insiders making a sale before things are released, and we want to detect them because that would be a insider trading or something like that. For this, we're going to basically pull. So we're going to make two. We're going to make two ingestion pipelines here, or I'm going to show you two. And these are what they're going to look like. They're going to be Bytewax data flows. So a data flow is a directed graph with processing nodes. One unique thing about Bytewax is it's a data parallel architecture instead of a task parallel architecture or a actor agent. So you can literally imagine the data flowing through each one of these steps. And so that's how the parallelism on Bytewax works. We won't get into it in depth, but essentially you split or partition your data. It goes into the individual workers. And then these steps here are all on each worker. And so the data moves through, and it will be exchanged if needed on a stateful step. One more piece that I now introduced and should mention, if you're not familiar with stateful versus stateless processing, it kind of is how it sounds. Stateful processing, you are managing or maintaining some idea or concept of state that you can use in that processing, whereas stateless has no idea. So an example of stateless is like, I'm getting emails and I'm just masking the email. I don't need to know what the other emails were. An example of stateful is potentially a window. So let's say every 5 seconds, for example, for stock tickers. So we're getting a bunch of stock information or price information, sorry, or maybe order information, and we want to turn that into discrete chunks, windows over time, and do something to it. Take the average, high, low, whatever it might be. So that's the difference between stateful and stateless, because in that second example, you would need to know what has happened in the past in order to build that window. Okay, so we're going to make two custom connectors, and I'm going to flip over to the code in a second. So one is going to be these SEC filings, and the other is going to be a WebSocket of financial news from Alpaca. So what is SEC and how do you get these filings, and what are they? So I think I mentioned this. The SEC has this thing called Edgar. This is where all of the financial filings data exists, and they have an API where you can request the most current filings. And so this is yesterday's. I think I did this at the end of yesterday. So you can see there are a shitload of filings. You can have 3,000 to 6,000 filings in a day. It depends. You can have even more. And there are a bunch of different types. You have 4, 8K, 6K, 1SA, blah, 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 Def 14A. Some of these, and they're all different sizes, and they have pictures, and there's and they can be 30 pages long or 60 pages long, and there can be a ton of information in there, and which is what we're going to use Unstructured to help us parse through. But so we don't care about all of these because not all of these actually have any meaning. So we're just going to focus on a few. If you clicked on this link here, it'll take you through to Form 4. Form 4 is when someone is buying stock. So if we looked at what the information we get from something like this is not so much information. It's not a ton of information in this, and it is quite structured. So this one's kind of easy, but we don't really know from the title. We don't really know what's going on here. So we'll deal with that in our processing pipeline. And then the other one I mentioned was a WebSocket. So it's really easy to create a WebSocket consumer Bytewax. So we'll stream the news from this Alpaca service. If you're not familiar with Alpaca, it's like a API for trading, where you can open a bunch of accounts, and I think you can almost make your own little brokerage thing. I don't know. I'm not a finance person, so some of this is me just trying to learn on the fly. But we're going to basically get all these Benzinga news, and we're going to process those downstream, because you can see it's like there's a bunch of HTML blocked in there. So we'll have to unescape some of that and do some special stuff. Okay, so let's flip back over to what this looks like. So the first component of the pipeline is an input. We have two inputs. Most often when you're dealing with input, whether it be a stream or something in real time, you're usually still polling something. So we are effectively turning an HTTP endpoint into a stream by using a polling input source. So here we have an SEC input source, and I'll kind of walk through I'll walk through what's going on here. The first thing is that if you ever want to scrape the SEC, you have to follow their instructions for the header and provide a user agent with your organization in it, or they'll block you. Second, we're providing some parameters here. So basically, we're creating this request. So every X number of seconds, X to be determined by us, we will request a RSS feed, essentially, an Atom RSS feed of all the most recent filings. And then we'll turn those, that will be part of our stream. So we'll be passing those downstream. So that's what a custom connector looks like in Bytewax. You can make custom connectors to virtually anything, but it's a way you declare how your the shape of your input. So like how many partitions does it have? How do you poll it? If you're polling it, is there a wait interval that you need to provide? Is it replayable? Should you be tracking the offsets on how far along you've gone? So the other news source is Benzinga, and so we wrote another custom input here. This one's a little more involved because it has it's not as simple as a HTTP poll, but we're using an async WebSocket library, and so we're connecting to the WebSocket, subscribing, and then Bytewax will consume, and that's what our stream is. So we have two separate files going on here. This one I'm going to show you is just a connector, and then we'll move on because the rest of the flow is really straightforward. Sometimes you get more than one thing returned, so we're flattening that with a flat map operator. I should say Bytewax has this, everything's an operator in Bytewax. Operators are essentially how you control the flow of data through the data flow. So basically we're just flat mapping those and we're just outputting these. I've commented out the way that you would do it to Kafka, but that's how you would write out to Kafka. And Bytewax is really straightforward. Under the hood, we're kind of dealing with all the things you need to. And then here I'm just outputting to a file sync, which is another connector that's included in the Bytewax library that allows you to write out to any file. Okay, so let's jump back to SEC, and I should take a second here and look if there are questions. Is this code available? Yes. Yes, this code is available. It's in the GitHub repo, which I think someone...
I'll drop it in the chat. No worries.
Okay. Okay, so back to this code, our Edgar scraper. So we request the most recent filings and we get back an RSS feed of a page of data. Then we're going to parse through that. So we have this stream handle we have here is from our input. Now we're going to parse that. We're going to use an operator called a map operator, well, flat map actually. So we're going to use a flat map operator again. So map is the idea of just like changing one piece of data at a time. Flat map just means like you have a list of it, but you want to send one piece at a time downstream. So this code here is taking the RSS feed and finding all of our filings and creating an object for those. It's a tuple with a dictionary, and in the dictionary we have the filing ID, which would be, it's not shown here, but There's a filing ID for everyone. If you click through to the HTML, that's like this thing here. I think it's this whole thing. So filing ID, the title of the filing, a link to it, which will be used in the after we write it out to Kafka, and also used down below for enrichment. The CIK is super annoying. CIK is just a unique identifier that the SEC uses. So it doesn't map necessarily to a company because it might be an individual who's doing the filing. So it's just a random name, and we'll have to a random number, and we'll have to figure out how it ties up to a company. And then the form type. So our next stream handle we have here is the output of this flat map, which is a bunch of these. The next thing we're going to do is use a stateful step. So because we're repeatedly polling this endpoint, we actually would get duplicates of data. So we're going to dedupe the data here before we put it in Kafka, so that, or Kafka in this case in JSON lines file, but in Kafka. That way, for everyone consuming downstream, we've done the hard work of deduplicating all of this, and they'll just have consistently the most, the newest available data. All we're doing here, so stateful map is like a map step again, but where we have an idea of state. So what we're doing is we're saying, okay, take the filing identifier and store that in a list. And then if I get a new filing that comes in, check if that exists in the list. If it does, return both the state object and then what I'm passing downstream. And then if it doesn't exist, add the filing ID to the state and then pass it downstream. So at this point we have only the unique filings left in the stream. Now we're going to go back to revisit this CIK to ticker stuff. So there's another file that just has and this is in the code too. It has company tickers matched to CIK. So I load these all into memory so that we can access them in this next step in the data flow. So the next step in the data flow is a little bit convoluted. It's another map step, filter map, and I'll explain filter map in a second. It's another map step, and we're going to do two things. First, we're going to see if there is if it's a company filing. So if it's like a quarterly filing by a company or something like that, or an annual filing, then we're going to take the CIK and we're going to match it to the ticker from our little lookup, and then we're going to pass that downstream. If it's a certain type of filing that we care about that we know won't have a company associated to it that has a stock ticker and is publicly traded, which would be 534, which are insider buys and sells, or not insider, just buys and sells, can be insider or not. So if it's one of those, we're actually going to make a request for the actual document. So that's like this one here. So we're going to make a request for this actual document. So we're going to pull this thing down and we're going to look for the issuer trading symbol. So that's what we're doing here. There's a little regex where we find issuer trading symbol, find them all if there's more than one, and then pass them back. And so that gives us a ticker associated with the filing. And now we can move on. The reason we want a ticker is that all of our news data is by ticker. All of the stock ticker price information will be by ticker. And when I say ticker, it's companies. And our questions that we might have downstream and why we're like building this whole thing would be reports about what has happened for a particular ticker. So like we might have questions about why the market went up or down, or just give me a report on what happened today with a certain company. All right, so filter map means when you're doing a map step, if for some reason there's data you don't want to keep in the stream, or it's like null, this allows you to return none. And if you return none, it will just remove it from the stream. So everywhere we return none, we'll leave from this stream handle, it will no longer exist. All right, we'll skip this serialization. That's required if you're putting it into Kafka. Serialization for Kafka. So that's basically putting this into a Kafka sync message, and then you'd be able to use the Kafka sync down here. We're just using the file sync again and writing this out. All right, that's it. That's all. I mean, I can show you how this thing runs if you're interested, but it's just going to make a new thing. So these are a bunch of warnings and info, and up here you would see filings, and then it would just keep getting new filings every, I think it's 10 seconds, but not sure. Yeah, so that's that. I will stop here.
Great, thank you so much, Zander. So I'm gonna go ahead and start with the next phase, which is how we took the data that came from that Kafka source and then populated the Azure AI search vector database. So before I jump in, so I just want to do a little bit of a recap of what we've seen so far. So we had a chance to learn what Bytewax is as our stream processing, as our stream processor in Python. We had a chance to see the Azure portal, and we had a chance to get some familiarity with the SEC filing information that we're getting from our Kafka source. So now I'm going to go ahead and take the next step. And I'm going to go ahead and walk you through the process we followed to actually take that JSON line file from our ingestion pipeline and start applying the solution from Unstructured and Azure services to populate a production-ready vector DB. So for this piece, I know there's quite a bit of information that we're throwing at you, so we've made the code available. We're going to be providing the recording. And because I'm going to be introducing a few new concepts, before I jump into the code, I want to show you first some of the key concepts and strategies that we used to integrate the different services in a way that we could run our pipeline in real time. So that is my goal now. I'm going to go ahead and start to share the screen. Present. Okay, so Zander had a chance to walk us through the first phase of the pipeline, which was ingestion, and he showed us some of the custom connectors that he built to integrate the data. Some of these custom connectors included accessing data from the SEC. Some of the challenges that we found when we were extracting data from SEC included the time limit for how many calls we can make, and also SEC likes knowing who's making the calls. So some of the code that we shared was to adapt to our needs for the SEC filing. Of course, if you're trying to parse or extract data from a different source, you might need to change this, but the base structure is right there. So I'm now going to move on to the next phase in our architecture, which is listening or hearing from absorbing or taking as input the data from our Kafka sources and actually extracting the content from the URLs. So in this particular solution, I'm going to be talking about the overall strategy that we implemented that allowed us to incorporate Unstructured, Azure, and Bytewax into a real-time pipeline. So let's jump in. So our challenge was to take the services from Unstructured for parsing data from these web pages, and I'll show you what the data looks like and why sort of how ugly it is and why we need the parsing. And then within the code, we're also going to have a chance to see where Azure AI services came in. So the goal for us was to integrate the embedding models to take the data from Unstructured and transform it from this text-based data into numerical data. If you're like, why are we doing this? Just as a very quick recap, when it comes to RAG and building these LLM-based systems, remember, this all goes back to this our transformer architecture, where the transformer is dealing primarily with tokens. And so these pipelines that we're going to be introducing and the concept of pipeline that I'm going to be introducing you to is reflecting that indexing process or the indexing stages, which is we have our data extraction, we're going to clean it, we're going to chunk it, and then we're going to apply an embedding model on our data to transform our data from text into numerical format. These numbers or vectors are then going to be stored on Azure AI Search, and it is what we can then use to retrieve appropriate information through the use of an LLM. So that is the overall strategy or the overall steps that we're going to follow. The challenge we had was integrate these different technologies using Python, such that the end result is a real-time indexing pipeline that populates Azure AI Search. So that is what I'm going to be showing you next. So for the data, I'm gonna exit. Oh, I'm just gonna exit here a little bit and just show you what the data looks like. So once we ran these ingestion pipelines, the end result is these JSON line files or structures that contain information on whether there's a ticker, and then a blob that tells us the ID, the title, the actual link to the URL, and then the form type. If I visit one of these URLs, this is what the SEC filings or one of these URLs look like. So this table in and of itself isn't very interesting, but the information that we care about lives inside these HTML, XML, and TXT files. So this primary doc is kind of ugly. Let's just go here. So we have these forms, and our goal is to extract the information from these forms. Now, this information is encoded inside of these web pages. So in here, you see like a lot of dirty is one way to say it. I have all these tags. I have all this HTML structure. I don't actually care about this HTML structure. I care about the content. So our goal is going to be to leverage Unstructured to get this information and store it as vector format. I'll go back to share and present. Okay, now in terms of the strategy we follow to incorporate, so I had to spend a little bit of time thinking, okay, so I want to use a Python-based resource that is compatible and works well with the data flow paradigm that we follow at Bytewax, that allows me both to easily connect to a number of different Azure AI services, but that also allows me to build custom functionality for my use case. So the strategy that I used for this particular piece of the solution was to use an LLM orchestrator. And in my case, there's many out there. We have LangChain, we have Llama Index, there's PromptFlow, there's lots of different services. The one I picked for this specific use case was Haystack. The reason for me picking this is the way they model RAG is as directed graphs, and they have a very strong focus on pipeline design and construction. So this specific design that they follow, we found was highly compatible with Bytewax. And one of the neat features that we found is usually within Bytewax, the way we work is we either build a class or we build a function, and then we plug it into our data flow through these map operators. And typically these map operators will be one step in the pipeline, right? They will be, data extraction, data cleaning, data chunking, data indexing, data storage. But what we found with these Haystack pipelines is that we can actually plug an entire pipeline as one of our map operators, which means we can go from data extraction from our Kafka source to the vector within one step as part of the pipeline, and then add a sink to write the data onto our Azure services. So this is the technique that we used. I found the compatibility between the two frameworks made this basically seamless. I was able to just plug a pipeline without any issues. So I'm quite excited to show. It is a little bit of a wrapping your head around it. So I'm just going to provide a bit of context, and they'll get to see what the actual components look like. So the strategy we used is we built a custom component for the unstructured and Azure AI functionality. Basically, what we did is we built a custom component that would take that URL and apply the unstructured functionality to extract and chunk the data. And then we used an out-of-the-box component to apply an Azure AI embedding model to the chunked data. Once we have our custom component, we can connect the custom component into a pipeline. I'll show you what that looks like in a bit. And the piece that I think maybe is a little bit more wrapping your head around this is one of the functionalities behind Haystack is the way we build custom components is just as a class with the run method, but they're also giving us the opportunity to define a pipeline as a custom component. This is the property or the functionality that we exploited within Bytewax, because what it basically meant is that our pipelines were open to taking as input Bytewax events. So instead of listening to a batch of data, it's just going to be listening to one Bytewax event, and then it's just going to do the processing. So this is what enables us to plug our pipeline into the Bytewax data flow so seamlessly. So before I jump and actually show you what these look like, I just want to provide a bit more context. So another area that we exploited quite heavily were the use of the data structures that Haystack already provides. In this case, I think the biggest data structures that we exploited were the document stores, where once we extracted the text from the web pages, we wanted that in a document object. Other data structures that they support include streaming. So if we're dealing with something like audio or chat or even something like video, that is another data structure that they are supporting. And we didn't leverage as much their data structures for Q&A. I think we placed more of a stronger focus on extraction and storage at this phase. In terms of the Haystack component categories, so you can think about pipelines. Since they follow this directed approach, directed graph approach, you can think of pipelines as nodes, where the components are the nodes, and then the edges are just the direction that the pipeline is moving through. So if I think about data science 101, how do we process our data? We extract the data, we clean the data, we model the data, we save the data. So each of these is one of the components, and I just connect them in the right order. Because this particular framework is focused on retrieval augmented generation. The components, of course, reflect those steps. So for data processing, we have extraction, splitting, caching, etc. Embedding, we're just going to incorporate a model provider, in this case, Azure AI embedding models. And then for writing, in this case, we didn't actually use any of this functionality. We focused on writing custom functionality for connecting to the Azure database services. And of course, this has to happen at exactly the time I wanna read this. I'm gonna switch from here, and then I'm gonna go back to my sample notebook right here. Okay, so if I take a look at my building blocks, so here is what let's just go right here. So this is what me defining my components looks like. Okay, so in this case, this particular workflow is just me extracting the content of a web page and then putting it into a document, splitting the document, and then writing the content of that document onto a document store. So in here, I define my components. In here, I just define my pipeline, I add my components, and then I connect my components in the right order. This idea of the right order goes back to the key assumption of Haystack, which is modeling RAG as directed graphs, where I don't embed the whole document. I have to first convert it into document data structure, I clean it, I split it, then I apply my embedding. So in this case, connecting components in the right order simply means doing the operations in the order that makes sense. I convert from HTML to document, I clean it. Once I clean it, I split it. Once I split it, I embed it. Once I have embeddings, then I write my documents. This is the workflow that I'm following. And again, the strategy that we're following in this case is we're simply defining custom components for a functionality, where all this means is I'm writing a class. For the component decorator, I am adding a run method that allows me to say what I want the custom component to do. And that's it. That's all I have to do to define a custom component. And then the piece that I think maybe takes a little bit of time to wrap your head around is we can actually plug these pipelines into this custom component definition. So it's like having a pipeline inside a pipeline, if that makes sense. What this allows me to do is, if before I was connecting components into a pipeline, this basically means I can now connect different pipelines into more complex systems. So this is what it looks like for me to wrap a pipeline as a custom component. As before, I have my class definition, and I initialize my pipeline, and then I can just have a run method for my pipeline to run. This is the feature that we exploited, where in here, instead of taking a name as an input, we're going to be listening to a Bytewax event, and then we're going to be doing the processing based off of that. Okay, so I'm going to go back to here. Okay, so we saw that what we have are pipelines for data extraction, pre-processing, and indexing and retrieval. For this specific phase, we're going to be focusing on these 3 steps: extraction, pre-processing, and indexing. So as I showed you before, what it looks like is I initialize my components, I add the components to the pipeline, and then I connect them in the right order. We saw the custom component definition. And then we saw how we can define pipelines as custom components. Okay, so now I can actually jump in and show you what our unstructured and Azure AI custom components look like and how we put them together. So here is the class if I were to make a call to the signature of my custom component is just defined as a class. If you remember from Nina's slides, and this is actually very important because there's a lot of subtlety in here. There's different chunking strategies. There's different different strategies that the Azure Unstructured provides, and there's different models that we can use depending on the type of document that we're dealing with. For this specific pipeline, we didn't have time to explore that level of subtlety, but essentially what this type of functionality allows you to do is you can say, okay, so I want to chunk, let's say, my PDFs by page, but maybe I want to chunk my tables by passage, or maybe I want to use an embedding strategy that ranks them by similarity. So there's quite a bit of subtlety in terms of where you can take your unstructured classes and where you can take the functionality. So we just build it in a way that allows you to control that. If I take a look at some sample links, so for example, some of these SEC web pages, they sometimes just have an HTML page that has a table. That's one of the kinds of links we might see. But sometimes, sometimes when we go take a look at this page, sometimes it's a form or it's a document of a different structure. So here's where that subtlety comes in, where the different kinds of links might need to be processed differently. So the strategy that you can implement in this case is to define the custom component and apply it to the page that have that specific logic. This will mean basically you'll have different streams, and then you can merge those streams later on and then write those streams of data onto the vector DB. Let's just go here. If I wanted to, and I want to go back here and actually show you what my custom component looks like. So I'm going to go here to unstructured component. So this is a component that Nina and I co-authored, where the way we are defining our component is we are initializing it such that we pass our unstructured API key. We're passing the chunking strategy, the strategy for partitioning, and then the model. These are the base functionality, or the differences in terms of how we can treat the different kinds of documents that we see. And then for our run method, what we're doing is we're going to be creating our partition. And then once we create our partition in here, we pass the URL. The URL is going to then be extracted through a request call. And then that content, that raw HTML file that you're seeing, is then what Unstructured is going to read and is going to apply the strategy on. So the strategy is then going to see the page, it's going to extract the text, it's then going to chunk it, and then those chunks are what we're going to embed with Azure AI. So all of this is doing here is just some code for some additional data extraction. Again, we found that there might be some classes or some information within the raw data that we actually want to keep, like the ticker. So this is just more custom functionality, but the heart of this custom component lies here, where we're using unstructured partition parameters in the client to apply the partition strategy, the chunking strategy, and the model. In this case, you noticed that my default, if I go back here, you notice that my default was using by page with an auto strategy and my model YOLO X. So remember this YOLO X functionality. This is a multimodal vision model that allows me to detect. So as these models become more sophisticated, or as we have access to more models, of course, the functionality of our parsers become more sophisticated as well. Okay, other things that we added to our custom component included just a method for extracting the data from the SEC. Again, for the SEC filings, they like to know who's talking to them and who's making these requests. And they also like us to not spam them with requests. The initial solution we explored incorporated a sleep mechanism, but instead what Zander built is a simulator for adding that delay in between calls, which we'll get a chance to once I actually get to the data flow. But this is what our custom component for unstructured looks like. In this case, I used the haystack component decorator and the output types for the run method, and I can now plug this component into a pipeline. So this is what it looks like when I plug my component into a haystack pipeline. So in this case, I have my component whose specialty is to extract the content of a web page, in this case, the SEC filings, and apply a chunking strategy and a model to extract the content from that web page and just give me the text. I want to clean my document. So in this case, I can apply regular expressions to remove things like tags, to remove things like extra line breaks, etc. And then the next component I want to add is this Azure OpenAI document embedder. So if you remember Shagun's portion of the talk, when she was showing us the portal, when you create a service for an Azure model, the different services we created, the LLM, the embedding model, and Azure AI search. So this Azure OpenAI document embedder is using the Azure embedding model. And when you create the service on the portal and you go to the overview page, you'll get a chance to see the endpoint and you get to see the secrets. So we're just going to plug in our Azure endpoint and our secrets and the model name. If I go here to my portal, if I go here to Bytewax workshop, and I go here to overview, I would have to go to keys and endpoint. So you can get these from Azure by simply copying and pasting the appropriate information. That we're just getting it from here. That's all we're really doing. We just plug it into the information into the component. We can then initialize our components, plug the components together. In this case, I first want Unstructured to extract the information from the web page, chunk it and clean it. Once I clean it, I apply my embedder from Azure AI, and then I connect these two components in the right order. Unstructured to clean, clean to embed. Okay, so now that we defined our pipeline, or that we have the different components, so we have our custom component, we plug our component into a pipeline. Now this is a time where we leverage that strategy of defining a pipeline as a custom component. So in this case, the way we defined our custom component is we did the same. I'm just going to go right here. Brad custom pipeline. So in this case, what we've done is we defined this custom pipeline as a class. So in this case, I have my class JSON L reader. All this is doing is going to take my components in here. I have my instructor component, my cleaner, and my Azure AI embedder. And then to initialize a pipeline as a component itself, I simply define self.pipeline equals pipeline, and then apply the add components and connect using the same signature. Once this is done, for my run method, what I am assuming is the run method is going to be listening to a Bytewax event. I'll get to the data flow in a bit. And so what this means is just going to get one of the entries in the JSON line file, and then it's just going to do some processing. In this case, what I want my pipeline to execute. The pipeline is going to go extract the content of the URL, apply the unstructured component, clean it, apply the Azure AI component, and then what this gives me as a result is these document objects. Once I have my document objects, what I do is I transform my documents into a dictionary. You can think of this as a schema, depending on how, in this case, it is a schema because I have some nested data within my metadata. Someone asked a question earlier on about creating our own schema within the Azure AI search. So we're going to be using the same schema there. So what this custom pipeline is essentially doing is it's applying our unstructured and Azure AI services, and then it's returning the data as a JSON blob following the schema that we chose. That's all that this is doing. Okay, so all I'm showing here are the different methods for our custom pipeline functionality. And then if I want to take a look at the directed graph, or basically the steps, again, I showed you the order in which I'm listening to it. So this is what the indexing workflow looks like, where I start from my sources. In this case, I'm going to have, I'm going to be reading from these JSON line files, and I'm going to be receiving a URL as a form of, in string format. I apply my unstructured parser to the URL. This is going to return haystack document objects. These document objects contain the extracted text, but they also include metadata, including the URL, the number of, or the length of the content, any other information that I want to attach. I attach things like the symbol, etc. I apply my document cleaner to remove things like extra spaces, and then I apply my Azure OpenAI document embedder to transform the chunks into embedding format. And what this is going to return, again, I can either return it as a list of documents. In my case, I wanted to have it in JSON blob format or in a dictionary format. So I just added an extra method to apply that. And now we get to the exciting part, which is actually adding the pipeline to our data flow. So we went through this whole process of understanding how this framework works, and the key elements that we're exploiting are their data structures, their assumption for RAG as directed graphs, and their custom component functionality, where we can not only define custom components, but we can also define pipelines as custom components and then plug these pipelines into a Bytewax map. So all I do here is I initialize my custom pipeline, and then I can have a wrapper function where this event here corresponds to a Bytewax event. So my JSON reader is just going to run, and it's just going to receive as input my Bytewax event. Okay, so now that we got through the process of understanding what are the different pieces behind the scenes, I can actually tell you now how these pieces come together into a real-time Bytewax data flow. Remember, our challenge was to integrate the different technologies using Python in a way that allows us to easily manipulate and move the data from one phase to the other in real time. So here's where the real-time piece comes in. So in Bytewax, we start our data flows through this data flow class. This is basically us indicating, okay, we're about to start the process of moving data from one place to another in real time. So far, all I've shown you in terms of the custom components and the pipelines and all of that is sort of base functionality that I'm going to use, but I'm not actually running anything in real time yet. This is where the real time piece comes in. So what we've built is, remember, in this case, because we're dealing with data from SEC and SEC doesn't want us to spam their services, what we've added is a simulation source that allows us to read the content of my JSON line files. Of course, what we're doing here is we're adding this through a custom connector. So this idea of connectors is very, it's key depending on what you want to connect to. For the simulation source, of course, we're simulating with our local file. We have Kafka connector. So if what you want is you want to connect to your own Kafka instance, you plug in the Kafka connector in there instead, and then you listen directly to the Kafka instance instead of just the local file. I'm doing it locally for the purpose of the demonstration, but just so you know, you can actually plug these interchangeably depending on what you're listening to. So this first step is simply going to receive the flow, and I'm going to label it as input. And in this case, it's just going to receive the input source is going to be my simulation source, which is just adding a little bit of a delay in between the different calls to make sure that I'm not spamming the service. Once this is done, the next piece, of course, is to deserialize the data. So remember, if I go back to my data, this is what it looks like. I have a list that has the ticker information followed by a dictionary that has a bunch of information. So my first step is to deserialize it. In this case, what I did is we just have a function that extracts the data from the JSON object plus a bunch of different logic for handling error messages or if there's any issues within the process. The complete function looks something, let's just go to RAG custom pipeline. The complete function looks something like this. So all I'm doing is I am extracting the content of my JSON object, and I'm just adding a little bit of extra logic if something fails. In this case, I had to deal with two different types of JSON line files. I'm just dealing with this. And then I want to add some logging information as well in case something goes wrong. So I just have this function to add it to the data flow. All I have to do is I go flow, input data, deserialize data is my next step. So I'm going to apply a map operator, and I'm going to label this deserialize. This map operator is going to receive the events from input data, and it's going to use the save deserialize function on them. Now, the next piece is adding our indexing pipeline. So the indexing pipeline is going to receive as input the deserialized data from the JSON line file. And then it's going to apply our custom pipeline with the Unstructured and Azure AI services to take the content from just an ugly URL to the embeddings of the content of that web page. So this is, I think, the functionality. In the data flow, it looks trivial, of course, because all we're doing is we're literally plugging a pipeline. But, you know, because we've seen before, we had to define our custom component, we put in a pipeline, we defined the pipeline as a custom component, and then added a run method that could listen to Bytewax. So within the data flow, this is now where the different pieces start to come together. And then for the last piece, which is writing to Azure AI through a Bytewax custom sync. So there's quite a bit of information here. It wasn't enough to put on a slide, so I'll walk you through what's going on. And Zander, I'll get you to jump in a bit as well and tell me more about the sync. But essentially, once we have our data in processed format and once we are happy with our embeddings, now the next step is actually to put them into the database. And in this case, whereas this extract HTML piece was carried entirely by the LLM orchestrator framework, this piece is carried now by Bytewax, where Bytewax is going to be taking the dictionary entries with the data, the content, and the embeddings, and then it's going to make sure that it's writing them appropriately onto a custom-defined connector. So I'm just going to go ahead and go back to my local data flow. So this is what my data flow looks like. So if I go to my custom connectors in here, what I've defined are these classes, simulation source. Yeah, so the simulation source partition, these are just classes to simulate the process of adding a delay. The other connectors that I added are the Azure search partition, where these classes are inheriting from Bytewax stateless sync partition, and they're simply just using requests to write to our Azure AI service. So in this case, what I've done is I have my schema. Remember this schema, and I'll get to the schema definition in a bit, but this is a schema that I have defined within my Azure AI service. So all this is doing is just making a post request to my Azure search AI service, and then writing the content of that dictionary onto it through a requests post method. So Zander, would you can you talk a little bit about how the stateless sync partition work and maybe why we're structuring things the way we are here?
Yeah, sure. You can keep sharing. I think so. The only thing I'll call out is you're probably thinking, oh, it's just an HTTP request. Why can't I just do that in a map step or something like that? The reason that we have gone through all the trouble to make the input and output APIs to build your own connectors is for the ability to partition and also for the ability for those to be stateful. In this case, Azure search partition is fairly straightforward. And so we're using a dynamic sync, and we're not using a fixed partition sync, and we're using a stateless sync partition. So the idea of a connector in Bytewax is you have two components. First, you have the what I guess we could call like a builder. So this is called at the beginning of the data flow to say, what do I need to do to consume or produce data to different sources and syncs? And that's what, in this case, that's what Azure Search Sync is. And so that's where you would send all your parameters, et cetera. In that, it has a build, has a list parts and a build parts method. And what each of those does is you can describe how the data is partitioned. So in this case, there's just one partition and it's just dynamic. So it's just going to build that Azure, I mean, you can have multiple partitions in this case or multiple workers, but it doesn't really matter because it's just a request. So it's how you deal with the parallelization of the inputs and the outputs and how you deal with creating things that could be exactly once. So you can do upserts, et cetera, and you can roll back and replay. This one, yeah, like I said, it's really straightforward. I think Laura covered what it is. It's you have the API endpoint, and you're just basically making a request there with the data.
All right, thank you so much, Zander. So, okay, so this is the machinery in place for us to go from the sources that we extracted with the ingestion pipelines and then populate our Azure Search AI instance. So now we get to the part of actually seeing the pieces come together. So I'm going to jump quickly to my Azure portal. So in here, what we've done is we just create a few services for the purpose of the workshop. We have our LLM and embedding models. We have our search service, and then we played with a little bit of other resources like the document intelligence, but in this case, the big focus here is on the LLM and embedding models from Azure AI and our search service. So if you recall from Shagun's presentation, Shagun had showed us here that we can manually create our index and then call it. So now we're going to show you how we do this through scripts. So of course, we can't actually start populating things before we add an index. So I'm just going to go back to the code. In here, what I have is some code to initialize our Azure index. In this case, we only need to run this specific script once, but here is where we defined our schema. In this case, what we need to do, what we're doing is we've added some imports from the Azure Search functionality. We are adding our endpoint credentials. Again, these ones you obtain once you create the services on the portal, and just make sure that you add, in this case, we're using an env file. If you have a different method, that's totally fine, but we're just using an env file where we are adding our variable names and the credentials. We're adding the key, the service, and the endpoint. From here, what we want to do to connect to the Azure portal is to create our client and add our credential. And then from here, we can start the process of adding the index client. So in this case, now I see a connection here. Remember, if I go back to my RAG custom pipeline, the way I am outputting my results is through this dictionary data structure where I have my ID, the content, the metadata, and the vector. So I made sure that schema and the schema that I create within Azure AI match. Of course, if you want to create a different schema, you can. And I actually would like to give a bit of a shout out to Shagun. So Shagun, if you could tell us a little bit more about what the type, searchable, retrievable, sortable, facetable, and key elements help us do and how they help us control our schema.
Yes, so these are actually necessary when you need to do, for example, keyword search. So you need to provide which field you want to search on as your keyword search. Similarly, filterable is basically if you want to filter out a couple of options or terms in your schema, you can have it as true in filterable, and these all will show up in your portal actually. When you go to your index definition, you will see that which fields are selected for filterable and face sorry, I cannot see your screen, just a second. So basically you can see whatever you have true or false here, it will be checked in your portal as well. Also, so these are necessary again if you, and this has to be taken care of when you actually define your schema, because once you check these options, you will not be able to modify later on. So whenever you define your schema for the first time, these have to be checked at that point, otherwise you will not be able to change it later on.
Thank you. Yeah, so I think there was a question in the chat previously about schema definition. Here's where this would happen. And as Shagun noted, there's lots of different ways to configure these depending on the functionality of your RAG pipeline and the kind of functionality you want incorporated. From here, we continue to configure the vector search configuration. So in this case, we're just passing information on the type of algorithm, the type of KNN vector search, any information on the profile. In this case, we're going to be working with my OpenAI vectorizer. And for the profile, we have the vector search profile, and we're using my OpenAI. And then for the vectorizers, we're going to be working with Azure OpenAI vectorizer, where we're passing the same name, the kind. And then in here, all we're passing are the credentials. In this case, we probably shouldn't have hard-coded this. Because this deployment ID actually corresponds to the way we named our resources. I'll make sure to clean that up and then add the right invariable variable name so you can just plug it in appropriately. But then this basically allows us to make a connection between our code and the service that we have deployed on the portal. From here, we have a bit more configuration in terms of the semantics. So we can create our semantic settings with our configuration. We can add our search index. In this case, I'm going to call it Bytewax index. And then I just create. So we're just going to go ahead and take a look at, we're going to start doing things live now. So Zander, everybody wish me luck. It's everybody knows live. That's always some things goes wrong in these. Okay, so I'm just going to run my init Azure index. Okay, so right now I don't have any indices. Okay, so I'm going to go ahead and add my indices. All right, So what this is going to do is it's going to run through the script, it's going to create the schema. So in this case, I have now these 4 lines correspond to the 4 different fields that I created. I have now created my Bytewax index search index. So I can go back to the portal in here, and then I now see here, no, come on. Okay, so I now see here that I have my Bytewax index in here. So let's just go to indices. Okay, so here's my Bytewax index. Right now, if I press search, there's nothing because I haven't actually populated the data source. Right now, it's just empty. But here's the exciting part. Okay, so what I'm going to do next is I'm going to go ahead and I'm going to run my Bytewax data flow. In this case, I am running my local data flow. The way we run these commands is through python-m bytewax.run, and then the name of the data flow, :flow. So in this case, just because we've given you so much information, I just want to tell you what this data flow is doing exactly. So what this data flow is we're initializing it as a RAG pipeline. We're reading input using our simulation source. In this case, I'm using a smaller subset of the data for the purpose of the demo. The news out and SEC files, these files are much larger. And of course, if you're listening to something like Kafka, of course, it's going to be much more. But for the purpose of the workshop, I'm just going to run a small sample data set for the simulation source. I'm going to apply a deserialization function. I apply my haystack pipeline, and then from here, I just output the content of the pipeline onto the sink, the Azure Search Sink. So we're just gonna go ahead and run it. And what you should be seeing now is, okay, so download succeeded. So this means that Unstructured was successful at getting the content from the URL. We then moved on to the next piece in the pipeline, which is to apply the embedding onto the chunks. So in this case, we are now making these calls to the Azure service for our OpenAI embedding model. And in this case, it's going to continue repeating this process. Notice how there's like a slight delay. This is from the simulation source slow mechanism that we implemented. And so now it has finished. So now when I go back here, I can refresh. And then when I hit search, I'm just gonna go ahead and hit search. So previously it was empty. It is now populated with our content. We have our title, and then we have the vectors. So through this workflow, we established a connection with the necessary tools to perform this kind of updates in real time. Through something like the simulation, of course, we only did it on the small data set. But as I mentioned before, if you want to do it on something like Kafka, instead of doing the simulation source, you plug in the Kafka connector, and now you're listening to your Kafka service, and then the rest stays the same. You can pretty much deserialize your data, apply the custom pipeline we built, and then dump that all on our custom search sink. And we populate our vector DB. Now, the last piece, which unfortunately I wish I had more time to go deeper, is the retrieval piece, which is I think the piece that most people are very excited about. So I'll only have a chance to show you how you can then make a connection and then start retrieving from Search AI services. Retrieving from Azure AI. So once we have populated our vector DB, what we have provided here is some code to help you through the process of making that connection. So as before, these keys are coming from the portal and from the services that you deployed. We initialize our client. And then in here, we just have a couple functions for performing text search on our vector DB. In this case, we're importing the vectorizable text query from our Azure Search documents models functionality. In this case, it's going to be performing the search against our Azure Search service endpoint. And it can we can provide what information to perform the search on. So notice here that I provide the meta, the key, and the content. Of course, within the metadata, at least the way we structured it, the metadata contains information on the URL. It contains the symbol associated to the form. So if it was a Microsoft stock, or if it was an Amazon stock or an S&P, that is inside the metadata. And then the content. If you wanted to make that a field that it searches in and of itself, of course, you can define this in the schema. We simply follow this convention because that's the schema we decided to define. But this basically means you can perform your searches, not just on the content, but also on the metadata fields as well. So if there's any keywords there that you want, the searching engine allows for this. And then from here, this is going to look very similar. If you've ever made an API call to something like OpenAI, remember we have our roles, we have our assistant who is in charge, basically the voice. Who do we want our AI model to be? In this case, you are an AI assistant that helps giving answers based on the provided data. You can make it a robo-advisor, you can make it a very serious person, you can make it someone who is an expert in the field and is generating reports. You can take the freedom to prompt the LLM how you want. And then for the user is going to provide a question based on the context. And then in the context here, we're passing our function vector text search. So in this case, we are giving our get answer functionality the ability to receive the user question. We have the prompt, and then we're leveraging Azure AI search to perform the searches based off of this function right here. From here, the only thing that we need to do is to create our client. So typically you would work with something like OpenAI. You create it using, I don't know, I think it's GPT 4.5 or GPT 3.5 Turbo, etc. So in this case, this model, again, we hard coded it. I should clean this up to make sure that this is not it. But this model name comes from your Azure service endpoint. You can control things like the temperature and the tokens, and then you can get an answer. So again, this goes back to now that we have our search system in place, or our indexing system in place, the next phase is to start iterating. Now, of course, there's lots of different areas to expand upon in here. One of these, of course, remember, if we think about some of the subtleties that we got from Unstructured, one, how the documents are being chunked relative to how successful the model is at retrieving. There's a lot of experimentation there, and there's a lot of tweaking and trying different things in terms of the different strategies and models that you use. To make the solution more robust, what we would recommend is, of course, adding things like guardrails, adding things like evaluation metrics to make sure that the model is responding things appropriately. And then Nina and Shagun, are there other areas or other aspects of the product or solution that you shared with the participants today that we could add to enhance the retrieval piece? Because I think we've focused the workshop mostly on the indexing piece. But of course, the part that's interesting is retrieval. So aside from simply prompting the LLM and adding our vector search, are there other techniques or strategies that you would recommend people to use when evaluating different strategies for embedding or different strategies for chunking? And I'll pass it to Nina first, and then Shagun can go.
Thanks, Laura. Yeah, I mean, I think there are a number of parameters that you can set within Unstructured for how you're chunking. So you could, if you wanted to, just do the standard approach, or I guess the baseline approach of just chunking by a certain document size. We typically recommend the chunking by title, but then you can also play around with setting the size of the chunks and the overlaps and things like that. So we have I think some information on that in our documentation on chunking. I'll share that in the chat shortly.
Thank you. And then Shagun, is there additional functionality within Azure AI search that we can leverage, or other services within the Azure suite to incorporate evaluation and performance of our RAG systems?
Yes. So there's a product called there's a service, sorry, not product, service in Azure called Prompt Flow, which is kind of a development end-to-end development tool. You can have whatever you have written in this code, like in the notebook, you can have the same thing going in the prompt flow, and there is an evaluation flow where you can have kind of a test data with prompt response pairs for your RAG pipeline, and you can use it as a test data to evaluate your flow. You can have different metrics like accuracy and responses. You can have different variation of your prompt engineering. So you need not call different cells, right? You can just integrate different type of prompting for the same RAG, and you can evaluate based on different prompting, which is performing better. For the chunking strategies, again, like I showed in the presentation, you can have the inbuilt text split skill in Azure AI Search, where you can provide whatever settings you want to provide for chunking, be it on line-wise, page-wise. If you want to chunk your JSON, if you want to chunk your CSV or extracted PDF document, whatever. So you can utilize that skill set. to chunk your data in whatever format you want. Additionally, also you can utilize LangChain integration with Azure AI services, right? You can do the semantic chunking, the inbuilt capability from LangChain. So sometimes I have seen most of like many of the healthcare customers, especially because they have relevancy across different documents and they have big documents, like insurance and healthcare industries, they try to do semantic chunking because there is no direct way to chunk the data based on the token size, right? Even the overlap doesn't work in that case. So I have seen people using semantic chunking as well. And again, you can define that semantic chunking on your own also, but there's inbuilt capability in LangChain that you can integrate with Azure AI Search.
Thank you.
So yeah, that's pretty much it.
All right. So I think with this, I'm gonna stop the share and just do an overview. And I think we're now.
There's one question, maybe
Yeah,
while
we're
we have
ready for
Shagun,
questions.
she
So
can answer.
yeah. Okay, sure. Go for it.
It's just around how do you manage the data volume in Azure AI search services? Is there, so let's say we're filling this thing with real-time data and we want to have a time to live value associated with data where we kind of drop off anything older than a certain date, or is there some strategy that's recommended?
So for the first of all, for the volume, I mean, it depends on the type of tier that you are using when you have deployed the service, right? The the scalability totally depends on the service tier that you have used for your Azure AI search. You can check different options basically for different tiers. What are the maximum size limits? How many documents you can index, in a second or in a short period of time. So that all depends on whatever settings you have used first to deploy your resource, and then you can. I mean, obviously, you can do some kind of asynchronous call, right? When you have parallel executions on your index, you can still try to find the answers and run the same index for different type of questions if that is the requirement in your use case. uh, if I mean, what like I personally use is if I have a bigger data size for the vector store, I try to create like multiple indices just to do that parallel work. And again, it totally depends if you can dissect your data like that or not. But I think it improves the performance overall if you can do it, because the bigger the index, the more time it takes to index the query and give you the answer.
Thank you. All right, so I'll just do final thoughts and then we can jump into questions. So some of the key things that we saw today included the functionality from Bytewax as our real-time processor, Unstructured as our document extraction and chunking, and then productionizing with Azure through services like Azure AI Search, Azure AI LLM and embedding models. And as Shagun noted, there's a number of different services that you can integrate if you'd like to manage and run the end-to-end workflow through services like Promptflow. We had an opportunity to take a look at one specific strategy that incorporates an LLM orchestrator into our data flow. Of course, if you work with different data orchestrators, then the goal would be to either build the classes or the functions to plug those that functionality within the data flow. But at the end of the day, what we wanted you to take away from this is that with Python, we can take data that changes in real time, we can ingest it through something like our custom connectors and the ingestion pipeline functionality that we shared, and then we can connect that stream of data into more modern NLP techniques around this idea of indexing pipelines, where we incorporated the use of different services and an orchestrator to apply transformations to the data, in this case, extraction, chunking, and embedding. And then we brought back how we can use the custom connectors to store the stream of data onto a production-ready service such as Azure AI Search. So with this, we can now move to the Q&A section of our workshop. So I'll just read the questions that haven't been answered, and then Nina, Shagun, and Zander, you can jump in as you see best. So if you have any questions or if there's anything that you'd like to discuss, please put it in the chat. Now's the time to ask questions. So the first question that I see doesn't have an answer is, if I am streaming current data into a vector database, what are the strategies and controls for managing it with Azure AI? Can I expunge older data or when the amount of data grows too large? Shagun?
I think that was the one that I
That was the one.
brought
Okay.
up. So it's Shoya answered that.
Okay, sorry about that. And then the slide's available somewhere. Yes, I'll make sure to share the link. Just one moment. I'll add the presentation link in a bit. I'll get to the next question. But I think there's still answers here. Okay, so how do you finalize your chunking strategy? Is it by running multiple simulations simultaneously? Okay, so maybe Nina and I can speak a little bit to this. So Nina, how would you start from experimentation of different chunking strategies to choosing the final one?
Yeah, so I would use an evaluation framework to see how the whole system works. So Shagun shared one below, for example, Azure's prompt flow. And then I would look at, let's say, the precision and recall of the generated responses of the RAG system, and try, different lengths of chunks and things like that to see which gives the best performance.
Okay, and then I think this is something that I did want to share, but I didn't have a chance to, is when so let's say that we're dealing with different kinds of data, or you want to apply different data processing strategies onto the data stream, how do you bring those together? So we didn't have a chance to go through this piece of the script, but essentially here. So if you had something like data sources that need to be explored in different ways, or you have different processes, let's say in this case, I don't have definition for these, but let's just say that I have two kinds of data sources and each needs to be processed differently. Let's say that you're dealing on one case with images and then the other with just PDFs, or you're dealing with the SEC filing news and then on the other dealing with a different kind of source. So you could create inputs for each of those. You can serialize, you can apply the different methods or the different processing techniques, and then you can merge them through a merge operator. So if you wanted to, for example, do your embedding in different ways, or you have identified different processes that you want to use, you can apply that in real time with the framework we've shared, and then merge them. And then after the merge, you could add the Azure Sync step where we're writing the final output onto our vector DB. I think this goes back to when you've identified the successful strategy and you're now at the data population stage. If you're at the experimentation stage, then I think utilizing tools like what Shagun and Nina mentioned for identifying the best strategy and then evaluating. Then once you know what the final answer is, then you can go back to this. Zander, is there anything you'd like to add?
No, there was one other question I answered in the thing, but then there was a new one that came up. Can you apply the same strategy to video streaming? For example, if you have a YouTube streaming and you can interact with the system by asking questions in real time or near real time. I mean, I can answer the Bytewax part of that. You can stream video, encoded or decoded video with Bytewax and get windows. This is a use case that I've seen before. Take a windowing approach, and then use an ML model to do object detection or something like that. But I think what you're asking is more along if you can then put that into a vector database and then ask questions. I think that it's possible. I'm
Yeah,
not sure if it's the best strategy, to be honest, because you have to re-index the vector database after all of the every time you input. So it might be delayed or it might be really big depending on what you have in the vector database.
And it also depends which part of the video you're seeking. If it's just the audio or if it's a mix of audio and vision, then at this point, the complex become the system becomes more complex because of the different types of embeddings you're using, but also it's unclear whether you're looking to answer questions about it or if you're looking to apply a multimodal model to detect things. So I think identifying the use case first, then identifying what tools are out there today that let you solve that problem, then bring real-time processing to the picture. Let's see. So, oh, it looks like there's lots of questions addressed in the chat. Okay, so it looks like most questions were answered in the chat. So, okay, so with the last few minutes, so Shagun, Nina, and Zander, are there final thoughts or takeaways that you'd like people to get from today, and maybe ways to continue the discussion if this is something that you're interested in?
Thanks everyone for joining. Yeah, this was fun. Great job.
Okay, slides. So I'll share the slides on the chat. Yeah, so thank you so much everyone for joining today. So what I'll do is I'll actually add the slides on the GitHub repository. So I'll just post the GitHub repo again. In the GitHub repo, there's the code, and I'll be adding the slides to the README. I think that'll be the easiest. This way we're not losing things. So let's just go right real-time RAG workshop. So here is our GitHub repository. If this is something that you are interested in, or if you have a retrieval augmented generation solution that you'd like to bring to production, or you'd like to bring stream processing into, please do connect with us on Slack and on LinkedIn. Our webpage is bytewax.io. We're always very, very happy to hear you out, hear your use case, and thank you so much, Zander, and to work with you. I think there was one more question I just saw. Are there any improvements that you would like to be there in Azure Search solution? I'm not sure I understand the specific question.
Yeah, even I'm not sure what the question is about. What kind of improvements?
I'm not sure. So maybe Sarah, I think your username is Saraswati. If you could expand a little bit more, that would be helpful. And then will we get a recording? We will be uploading this on our YouTube channel. So Zander, if you could repaste the URL to our YouTube channel so you can subscribe to us, and then we'll be posting it there soon.
I think there was one question about free access to Azure AI search for exploration. So I think when you set up, it depends on the free Azure subscription that you sign up for, and it gives you a little bit of credit. And I think you have to use the S0 tier to deploy that resource, and you have limited number of documents that you can process in the Azure AI search. So there's no specific way to get the free Azure AI search access. It totally depends on whether you have the free Azure subscription, like the trial subscription. If that is the case, then you get limited number of documents or limited size, basically, depending on the subscription.
Okay, thank you so much. All right, so I think this will be it for today's workshop then. So thank you so much for joining us. As I mentioned, we're very happy to continue the discussion. If retrieval augmented generation and real-time data is something that you're actively working on, we're always looking to collaborate with you on your solution. Please do connect with us either through our Slack. You can also connect with us on GitHub. You can connect with us on social media, and we're very happy to chat with you. I'd also like to give a shout out to Nina and Shagun for working with us as part of this engagement. So we had a chance to actively put together these scripts and this functionality to ensure that we can give it to you nice and clean, and you can test it, you can use it, you can apply it as you need. The workshop material is public, and we will be uploading the video on YouTube shortly. The updated slides will also be added to the README in the GitHub repo for our workshop. So if it's something that you'd like to have, we'll add it in the YouTube description as well, so you have it. So other than that, thank you so much, Zander. Thank you, Nina. Thank you, Shagun. And thank you, everybody, for joining us in today's workshop.
One last thing we didn't mention at the very beginning. There's a Slack channel You can find it on the
Yes.
workshop on our website. I'll also drop it in the link. If you have questions after the workshop about the workshop, there's a channel in the Slack that's just called workshop, I think. So workshop room, I think it's called. So if you have questions, you can go there and ask us.
Yep, I've added the invite to our Slack, so it should be good to go.
All right. Thanks, y'all.
All right. Thank you so much, everyone. Have a great rest of your day.
Thank you, everyone. Thank you.
Bye.
Thanks.
Bye.
Bye.